Hello, and welcome back to the third episode of the Cartesian tensor calculus of Euclidean metric spaces. In this episode, the mathematics is about to take off, as we will be discussing the Euclidean metric tensor and the Einstein Summation convention. We'll go ahead and begin by covering metric tensors. As we discussed before in a prior episode, when we impose a notion of distance on a topological space, we have a metric space. The notion of distance we impose on that space is then called the metric. We also discussed that this metric is referred to as a metric tensor, and it is indeed a tensor because it's invariant under coordinate transformations. For the flat Euclidean space R3, the metric of infinitesimal distances between points is given by the square of a line element. The line element gives the infinitesimal length of a line between displacement vectors. For a 3D Euclidean space in Cartesian coordinates, we have the following line element. So ds equals dx plus dy plus dz. To obtain the metric tensor from this line element, all we have to do is square the equation on both sides to produce a first fundamental form. So we have ds squared equals dx squared plus dy squared plus dz squared. This shows that the first fundamental form of Euclidean 3 space is a three-dimensional Pythagorean theorem. This fundamental form is the metric tensor of R3. We can call this metric a tensor lower g and its components g mu nu to provide notation for our focus of interest. Then we can represent the metric components using a 3x3 matrix with Cartesian coordinates. So g mu nu equals the following 3x3 matrix, where we have g sub the same coordinates on the diagonal and g sub varied coordinates on the off diagonals. Basis vectors of the space are always orthonormal. So if we have the dot product of basis vectors e sub mu and e sub nu, we get 1 if mu is equal to nu and 0 otherwise. This should start looking a bit familiar. With this information, we realize that the Euclidean metric tensor of three-dimensional space is a 3x3 identity matrix. So we have 1s in the diagonal and 0 elsewhere. So the Euclidean metric tensor can be rewritten as the Kronecker delta function, which itself is a rank 2 tensor. So g mu nu equals delta mu nu. With all of this considered, let's look back at our first fundamental form, otherwise known as our metric. This metric may be rewritten in terms of tensor components with sigma notation. So ds squared is equal to the discrete sum as mu ranges from 1 to 3 and as nu ranges from 1 to 3 of delta mu nu times dx upper mu times dx upper nu. We can combine these two discrete sums into a single sum over all mu and nu since we know what dimension we're working in. This is R3. And then, since we already know what we're implicitly summing over, we can just eliminate the sigma notation altogether. So all of this information is contained in delta mu nu times the contravariant differentials dx mu and dx nu. This is just another way to write our metric. So we just discovered our first example of the Einstein summation convention. Let's go over that now. There are three rules given by the Einstein Summation convention, which we will list here. 1. Repeated indices are implicitly summed over, as we just saw in the last example. 2. Vector components are given by upper indices, and basis vector components are given by lower indices. 3. Dual vector components are given by lower indices, and basis dual vector components are given by upper indices. These three rules will serve to make our lives much easier and make the following equations look a lot more condensed and elegant. Example number 1. Say we have a 3-vector V in R3. So V upper mu is given by the following column vector V1, V2, V3. We recall from rule number 2 that vector components are given by upper indices and basis vector components are given by lower indices. So V mu can be written as V1 times E sub x plus V2 times E sub y plus V3 times E sub z, where E is the basis vectors and the subindex are the component. We can now switch from x, y, and z to 1, 2, and 3 to make our notation look a little bit more symmetric in nature. With this out of the way, using the notion of linear algebra, we can just use sigma notation to represent all this information. So V upper mu is given by the discrete sum as mu ranges from 1 to 3 of V upper mu times E sub mu. And we remember rule number 1, repeated indices are implicitly summed over, so we can get rid of the sigma notation to make something look a lot simpler. So V upper mu is equal to V upper mu times E sub mu. We'll have a second example here. Say we have a dual 3-vector V star in R3. So V star sub mu is equal to the following row vector V1, V2, V3. We recall from rule number 3 that dual vector components are given by lower indices and basis dual vector components are given by upper indices, yielding the following equation. This is like a reverse of what happened to our normal vector. We'll use the exact same analogy that we used before to do a numerical substitution over x, y, and z using 1, 2, and 3. And then we can use sigma notation to sum this up. And of course, if we recall rule number 1, repeated indices are once again implicitly summed over. So we get a simplified equation for all that information. So now we know what a vector and dual vector look like in Einstein summation. Example number 3. Now we want to see what happens when we have a dual vector acting on a vector. So we have a dual vector V star sub sigma acting on a vector V upper lambda. So using the rules that we learned in the prior 2 slides, V star sub sigma is equal to V sub sigma times the in this case, we have a contravariant basis vector, E of sigma. And then we have, of course, the contravariant vector, V lambda, equaling V lambda times the covariant basis vector, E sub lambda. So we can just write this multiplication out explicitly. We can organize this using the properties of linearity and the fact that these are commutative to we can have our vector and our covectors or dual vectors in one location, and then we can also pair our basis vectors together as follows. So this looks more neatly organized, at least in my opinion it is. And since we're in an orthonormal basis, our basis vectors E sigma and E lambda multiply together into a dot product that yields a Kronecker delta function. Now, since we have two indices here that are the same across the contravariant vector and the delta function, namely lambda, we can cancel them out, and then sigma comes over to take the place of lambda in the contravariant vector. So V star sub sigma acting on V lambda is equal to V sub sigma times V upper sigma. The same is then true for the opposite multiplication. So V acting on V star is the same as V star acting on V. Example number 4. We want to consider Einstein summation in terms of a metric tensor for a 10-dimensional Euclidean space called R10. We're going to realize very quickly the power of Einstein summation in this example. So we'll consider the first fundamental form, or in other words, the metric for this space. So it's good to go ahead and understand your Greek letters. So I'll go ahead and read through these. This is dx squared plus dy squared plus dz squared, as you already know. And then we have d alpha squared plus d beta squared plus d epsilon squared plus d rho squared plus d lambda squared plus d sigma squared plus d omega squared. If you're getting into tensor calculus, it's a good idea to have your Greek alphabet down. So all of this can actually be represented in a 10 by 10 matrix, which is the metric tensor components. So this looks extremely intimidating. And of course, no one wants to actually write all of this out every single time they're working with this matrix or this differential form above, which is our first fundamental form. The good news is that we're in an orthonormal basis. So everything that's not in the diagonal goes to 0. So we're left with only 10 components that matter out of these 100 total components. So since this is a flat space with an orthonormal basis, as I mentioned, this huge matrix becomes a 10 by 10 identity matrix described by the Kronecker delta function. So then we can just write our metric as the following. So all of that information that you saw from both of those examples on the prior slide are given by this simplified equation. We know that we're summing over 10 dimensions, so we can combine this into a single discrete sum over all mu and nu. And then going back to rule number 1, where repeated indices are implicitly summed over, and we realize basically that all of the information that we saw on the last slide can be condensed into a much simpler equation. So ds squared equals delta sub mu nu times dx upper mu times dx upper nu. So no matter what dimension that we're working in, this equation actually holds, so long as you know what dimension you're working in. Now here are some other examples. We can express a second rank tensor in terms of a rank 3 tensor as long as we have a contravariant vector to eliminate one of the indices. We can then go ahead and express that as a rank 4 tensor as long as we have 2 contravariant vectors available to cancel 2 indices. And then for covariant tensors, we can represent that as a rank 4 or rank 3 tensor or a rank 5 tensor as long as we have an associated amount of covariant vectors to cancel out the proper amount of indices. So for a rank 4 tensor to reduce down to a rank 2 tensor, we're going to need 2 covariant indices, etc., etc. For a mixed tensor, we just need the proper combination of contravariant and covariant vectors canceling out indices. And then we can consider a metric tensor acting on a contravariant tensor, where in this case, the mu's cancel out to yield T upper sigma lambda sub mu. And then we have what's called an inverse metric tensor, which is just a contravariant variation of the metric tensor, acting, in this case, on a mixed tensor to give T upper sigma sub lambda, where the mu and nu cancel using Einstein summation. What happens when we have a metric tensor acting on another inverse metric tensor? So if we have G mu nu acting on G upper mu phi, and that gives the Kronecker delta function in terms of phi and nu. So then what happens when we have G mu nu acting on G upper mu nu? Well, all we get is the trace of the identity matrix. So in other words, the trace of the Kronecker delta function, and that just gives you the dimension of the space you're working in. So if we are in R3, as much of our series will be based on, the trace of the Kronecker delta or identity matrix is just 3, and so our space is 3-dimensional. This works, of course, in any dimension. So in R10, the trace of I is just 10. We'll finish this video by showing you some practice problems you should definitely have down before moving on to the next video. There will be 6 of them. Number 1, find the trace of G mu nu in R1337, the 1337-dimensional Euclidean space. 2, express the first fundamental form of the space R5. Number 3, is the Kronecker delta function always equal to the components of an identity matrix and Euclidean metric tensor? Number 4, show that V star sub phi acting on V upper psi is equal to V upper psi acting on V star sub phi. Basically, I'm just asking you to show the commutativity between the dual vector and the vector. Number 5, analyze the metric tensor G mu nu acting on the covariant rank 4 tensor T upper mu lambda sigma omega. And to really hone in all the skills shown in this video, you should be able to work through this final equation. Number 6, show that the following tensor equation holds. So we have the Kronecker delta function upper mu lower mu, or nu, acting on T sub mu sigma minus T sub nu sigma equals the quantity R upper mu nu sigma acting on the covariant vector V sub sigma minus R upper mu nu sigma sub lambda acting on the contravariant vector V upper lambda and the covariant vector V sub sigma plus the quantity G upper mu nu acting on F upper sigma lambda sub mu nu minus G mu nu times F upper mu nu sigma lambda. If you can work through that equation, I guarantee you'll have everything you need to continue making success within this series. Thanks for watching this video. And as always, if you have any questions, feel free to reach out to me in the comments below.